Today we're going to talk about 5 theorems that involve perpendicular lines, and what I want you to pay attention to is the if part, the given part, and the then part, the conclusion, because that's what I'm going to be checking to see if you understand. This first theorem, it doesn't have a special name, Theorem 3.8, says that if two lines intersect to form a linear pair of congruent angles. And so I want you to look at this picture, and I want you to see the setup. We have a linear pair, angles 1 and 2 are a linear pair, and they're congruent, swoop, swoop. And doesn't that mean that if they're going to add up to 180 and they're both congruent, that they'd both have to be 90 degrees? So the punchline to this theorem, the conclusion, is that the lines are perpendicular. If angle 1 is congruent to angle 2 in a situation that looks like that, we can say the lines are perpendicular using the Theorem 3.8. The next one, Theorem 3.9. If two lines are perpendicular, then they intersect to form. So the picture is going to involve some perpendicular lines. You would have to know they were perpendicular. And if you know they're perpendicular, then you have all 4 of those angles being right angles. If A is perpendicular to B, then angles 1, 2, 3, and 4 are all right angles. In the diagram at the right, we have perpendicular lines. What can we conclude about angle 1 and angle 2? If we use, which theorem would apply in this setup? The given part is that we have perpendicular lines, so that would have been the Theorem 3.9. If two lines are perpendicular, then they intersect to form 4 right angles. So what can we conclude? The conclusion is that angle 1 and angle 2 are right angles by Theorem 3.9. Next one, in the diagram at the right, angle 1 is congruent to angle 2, and we can see from the picture that those are a linear pair. What can we conclude about A and B, those lines? Well, the setup looks just like the picture from Theorem 3.8. If two lines intersect to form a linear pair of congruent angles, then what can we conclude? The lines are perpendicular. Line A is perpendicular to line B, and that was using Theorem 3.8. Third theorem of the day, Theorem 3.10. If two sides of two adjacent acute angles are perpendicular, that's a lot, so the picture helps me. The setup is the two sides of our adjacent angles are perpendicular. So angle 1 and 2 are adjacent, and 2 of their sides are perpendicular. Then the angles, what could we say about angle 1 and angle 2? Well, we have that perpendicular, so we can say that angle 1 and angle 2 are complementary to each other. If line BA is perpendicular to line BC, then angle 1 and 2 are complementary. Let's practice using some of these. In the diagram at the right, angle 1 is congruent to angle 2, that's already marked on there. And we are supposed to prove that angle 3 and 4 are complementary. So it's got the given already filled in. And if we look at Theorem 3.8, doesn't that go from congruent angles to perpendicular lines? So let's look at angle 1 and 2 again. Do you see how that's a linear pair of congruent angles, just like Theorem 3.8 says? So our conclusion is that we have perpendicular lines. And then what theorem is it that takes us from perpendicular lines to complementary angles? We can see that angle 3 and angle 4 are set up right in those perpendicular lines. Again, it helps me to look at the diagram. What goes from perpendicular to complementary? That would have been Theorem 3.10. We're going to use that same diagram again. Given that angles 1 and 2 are congruent, we're going to try to prove that angle QPS and angle 1 are right angles. QPS and angle 1 are this angle and this angle. Again, we were given that angle 1 was congruent to angle 2. What lets us say that because those are congruent, then we have perpendicular lines? Angle 1 and 2 was our linear pair of congruent angles, so again, that's theorem 3.8. And now that we have perpendicular lines, which theorem says that if you have perpendicular lines, then you have right angles? The definition of a perpendicular line says that the lines intersect at a right angle. So this new theorem is a little more strong. Do you remember the one that says if you have perpendicular lines, then you have 4 right angles? We aren't listing all 4 here, but that's the one we want to use, theorem 3.10. If 2 lines are perpendicular, then they intersect to form 4 right angles. Of course, I don't expect you to memorize these theorems. That's why I've already printed them on your reasons list. And the last 2, this one's called the perpendicular transversal theorem. It actually has a name. You can call it theorem 3.11 if you'd like. If a transversal is perpendicular to one of 2 parallel lines. So here's our transversal that's crossing through those parallel lines. And this says that if it's perpendicular to one of the parallel lines, then it's perpendicular to the other. And I think that makes sense, because if that's a right angle, wouldn't my corresponding angle right there also have to be a right angle? So yes, it's going to be perpendicular to line K as well. And theorem 3.12, lines perpendicular to a transversal theorem. This one, in a plane, if 2 lines are perpendicular to the same line, so in the picture M and N are both perpendicular to P, then they, meaning lines M and N, are parallel to each other. And again, I don't think that's too surprising, because we know a lot about how corresponding angles are going to give us parallel lines. Our corresponding angles happen to be right angles, but that doesn't matter much, so double perpendiculars are going to tell us that those are parallel. Determine which lines must be parallel in this diagram and explain your reasoning. So I actually see a bunch that look parallel, but we have to think about what can we actually verify are parallel lines. The first one I think would be parallel. I think I could say that lines P and Q are parallel. And the reason I'm thinking that is because I'm seeing these 2 90-degree angles right here, right? Do you remember that theorem that says if P and Q are both perpendicular to the same line, then they're parallel to one another? That's the one I'm thinking. So I would say that P is parallel to Q. And which theorem was that? That was theorem 3.12. 2 lines perpendicular to the same line are parallel to each other. All right, what else is looking parallel over here? All 3 of these look parallel to me, S, T, and U. But I'm thinking, do you see how line U doesn't have any angles marked? It doesn't show that it could be slanted one way or another, and we would never know. So I'm thinking we can't say anything about line U, but I wonder if we can prove that S is parallel to T. Do you see anything? I think again, since S and T are both, do you see these 2? They're both perpendicular to the same line. So if S and T are both perpendicular to the same line, then we can say they're parallel to each other. You might have noticed that I wound up using the same reason both times, but let's go back. Do you know why that is? That's because the conclusion for this theorem is parallel lines. If I'm trying to prove that lines are parallel, that might be my only choice out of our new theorems. This one proves that lines are perpendicular. This one proves that angles are complementary. This one also proves that lines are perpendicular, and this one proves that we have right angles. So when I was asked to prove that lines are parallel using these new theorems, that was really my only choice, was theorem 3.12. Again, I want you to pay attention to what the if part and the then part are on these theorems. I don't know if this will seem obvious to you or not, but we wanted to make sure that everybody's measuring things the right way. If I asked you how far away is point A from line K, where would you measure? I would hope that you would measure straight down at a perpendicular. We know that's not how we would measure the height of someone. We wouldn't measure it all slanty. So if they are talking about the distance from a point to a line, they are talking about the perpendicular distance. Same thing when they're talking about how far apart are two parallel lines. We should always go for that shortest distance from line to line, which will wind up being perpendicular. We wouldn't want to go from here to here. That would be a longer length. We would want to be able to measure all of those the same, and no matter where we measure in a perpendicular way, we should get the same length, the same distance between those two parallels.